Okay, great. Well, hi everyone. I'm Greg, the founder and CEO of Oxen AI, and I'm here to talk about datasets and infrastructure for GRPO, and specifically how to train your own reasoning model with RL, and specifically on coding in Rust. So Rust is a nice language that has really good compilers and error messages. So we're going to be using that in the reinforcement learning. And I'll kind of walk you through just high level what DeepSeek-R1 did in their training, which you might have heard a couple times today. So I will go faster through that part. Then dive into what is GRPO, and then the fun part of what you need to run GRPO yourself, walking through a practical example of training this 3 billion parameter small language model specifically on Rust code. Uh, this model, spoiler alert, gets up to GPT 4.0 performance for a very small model. So that was pretty exciting. We'll walk through the training data, the hardware requirements, which if you're training small models, I think is really interesting to keep your costs down, and the specific reward functions that we used to train this model. But before I start, maybe a little interaction from the crowd here. Who here uses just foundation model APIs in their workflows? Most people. Is anybody using local or self-hosted models? Oh, even more. Nice. Who's done SFT on these models? Awesome. Anyone done reinforcement learning? One, two. And you guys have your own proprietary data sets for this, or using public data sets? Public? Currently making it. Awesome. Well, a little bit on myself. Like I said, founder and CEO of Oxen. I've been training language models before they were called large language models, so since 2013. Was a part of a small startup that got acquired into IBM Watson, but we were writing neural network libraries in C++ before TensorFlow or PyTorch or any of that. And I've been doing NLP, computer vision, uh, 3D asset generation, and reinforcement learning for over a decade. I also run a paper club on Fridays called Archive Dives, where we just get together and talk about research papers over Zoom. So if you ever want to join that, it's like dinner time for Europe and breakfast time for LA. And I am from Los Angeles, so traveled a good ways to be here. All of the experimentation and data sets that we did for this live in Oxen AI, which is my company. Uh, the main problems that Oxen solve are how do you version and share these massive data sets and massive model weights in a way that's like as easy to use as a GitHub. So we render multimodal data sets, allow you to query them, allow you to spin up notebooks on GPUs, train models, evaluate models, explore the data, generate synthetic data, and all of it is version controlled and in a beautiful UI. So I'll be talking about how I use that infrastructure within this to make all of these experiments really reproducible. So with that, let's dive into GRPO. And I always like to start with this diagram from the original Instruct GPT paper, which was the paper that led to ChatGPT. And so there's kind of three steps in this language model training process. There's the pre-training and supervised fine-tuning here on the right. So you go from a prompt to a response, and you do that over and over again. So that's kind of step one to even make the model output coherent thoughts. Step two is typically trying to train a reward model for this reinforcement learning loop. And so once you have a model that can output coherent thoughts, then you have that same model for one prompt, like explain the moon landing to a 6-year-old, generate a bunch of different responses for that one prompt. And you might have a human in the loop here saying D response is better than C is better than A, and kind of rank those and then train a separate model, which is also could be bootstrapped from an LLM. And you call this the reward model. And basically all this is doing is given these 4 answers, rank which one's the best. So once you have your supervised fine-tuning model and you have your reward model, you can put that into a reinforcement learning loop in step 3. In the case of ChatGPT, they used an algorithm called PPO, which will be important when we talk about GRPO because we'll take some concepts from there but make it a little more efficient. And that's kind of like the end-to-end flow. So there's a lot of models, a lot of data sets, and a lot of training that goes into putting this end-to-end RL into practice. And so big labs like OpenAI and Anthropic had been doing this process for a while, and people were wondering if there would ever be an open source version that competed. And kind of at the beginning of the year, we all saw R1 drop, and with really impressive numbers, especially in this reasoning type of scenario. And the way I like to think of reasoning is LLM without reasoning might go immediately to the answer. So if you had a prompt like if a car is moving 30 miles per hour or kilometers per hour and it travels for 20 minutes, how far is it gone? Uh, an LLM without reasoning will just immediately output that answer. And an LLM with reasoning might break it down step by step, put out the equation for distance equals speed times time, figure out what the speed is, figure out what the time is, figure out the equation, and then output the right answer. So walk through and kind of do more reasoning. And what's really cool about this, especially in a reinforcement learning workflow, is you can kind of let the model figure out what the steps should be in between these think tokens here. And you don't have to explicitly tell it how to come to the correct answer, but you still want some correct, like verifiable answer at the end. So we'll talk about how that all works. And what they kind of found in the R1 and especially in the R10 model is if you do this reasoning step by step through math problems, they figured out that the model on its own kind of would self-correct as it was going through the reasoning and be able to stop, backtrack, try to solve the problem again. And that was kind of their aha moment of, wow, we didn't explicitly tell it to wait and try something else, but it kind of did it on its own. And so R1 extended those three diagrams that I showed at the beginning by alternating between the supervised fine-tuning, a GRPO, RL reasoning step, supervised fine-tuning again, and then RL again. And so the blue boxes here are kind of prompt response pairs, and then the orange boxes are reinforcement learning. And the reason they do this, the cold start is very similar to why they would do the supervised fine tuning at the start of any run just to get coherent prompts and responses out. But in this case, they have two separate reinforcement learning loops. The first one is that reasoning one, so figuring out how to put the think tokens in there, have a chain of thought, and then come to the answer. Then they do another pass of this supervised fine tuning with a bunch of synthetic data, so 800,000 examples where they would run actually the V3 model, not the R1 model, to figure out what these best chain of thoughts were, and then retrain on the best ones. And then finally, they ran reinforcement learning again, less for reasoning, but more for optimizing for helpfulness and harmlessness. And that one uses an LLM as a judge as the reward model to tell whether or not it was helpful or harmless. And so let's dive into these orange boxes a little deeper. It was actually the DeepSeek math paper that first introduced how they used GRPO in the training. And it's this diagram that's kind of the key here. So you can see PPO on the top and GRPO on the bottom. And for both of them, you have a queue go in, which is your prompt or your query. And for PPO, you'll have an output come out. You'll run that output through a reward model, through a reference model, which is a copy of the original model that you started training with, and through a value model to get a reward, a value, and then you do this advantage calculation that will give you the final score that comes out. But what I want to highlight here is you have a bunch of different LLMs in here. So say you had like a 70 billion parameter model, you have 70 billion parameters here, 70 billion parameters here, here, and here. So that's just like a lot of compute to have on your hardware. GRPO, on the other hand, will have one query come in and it'll generate those 4 responses like we talked about before. It still has this reference model and it still has a reward model that will give some scores out. The reference model here, you'll see there's this KL line, which stands for the KL divergence. And this is just making sure that your model doesn't drift too far from the original model as it's training. It doesn't come up with like crazy new strategies, but it is kind of expensive to have both of those. And then once you have the 4 ranked responses, you actually do a different calculation to compute the advantages. And we'll talk about the math behind that on subsequent slides. But you can think of, if you're solving like word math problems, these would be some example outputs where you have 4 different stabs at solving this word math problem. This is the correct answer here, or this is the question 4 times. This is the correct answer. This is 4 different reasoning traces that the model outputted, and then there's 4 different answers that the model outputted. And in this case, we're doing a generation size of 4. 2 of them were correct, 2 of them were incorrect, and we want the model to generate more that are correct. And it's pretty crazy nowadays with the TRL library and even the Virl library that we saw before here. You can do this whole training loop in like less than 10 lines of code, depending on how many reward functions that you define. And we'll dive into that a little more later of how practically you can do this. And so right here, you can see we have our GRPO trainer and we have a list of reward functions. So some simple examples of what that might look like are, you could just have regexes to try to get your model to do some of these things. So you could have one that says, hey, we need the model to output an opening reasoning tag, an end reasoning tag, an answer tag, and an end answer tag. 1, so it does all of its thought process in here, and then 2, we're going to be extracting the answer from a specific format at the end. And then you might have just a pure string match at the end of, okay, given what we extracted from the answer tag, does that match the correct answer that we had? And so this is an example of, we have 3 or just 2 functions here, I guess. We have the extract XML answer, the formatting reward function, and then the accuracy reward function. And so going back to that example that I kind of had in the data frame before, you might have a question that, you know, Mr. Curtis has 325 chickens, et cetera, how many egg-laying hens does Mr. Curtis have on his farm? And you might have 4 different outputs here. The first one has the fully formatted opening reasoning tag, closing reasoning tag, and answer. And the answer is correct. You might have one that has like the opening reasoning tag, closing reasoning tag, but no reasoning in here. So maybe you get that a score of 0.05. You might have one that just outputs the answer, that gets a score of 0. And you might have one that just has an opening reasoning tag and nothing else, and that has a score of 0. So then you take them, and this equation looks a little more intimidating than it actually is. But if we just put these 4 values that we saw before in an array, so this was the one that was correct, this was the one that was partially correct, and these were the 2 that were wrong. Kind of the main thing that you should keep your eye on here is this advantage function, which in the big equation here is right here. And so that's the value of the reward that you're on, subtracted by the mean of the reward of all of the rewards, and divided by the standard deviation of all of the rewards. And this is like a common function in machine learning to tell you how many standard deviations from the mean your score is. And so if you look at the actual outputs, the advantage of the first one would be 1.5, the advantage of the second one would be 0.3, and then these ones would get negative scores down here. And that scales really well if you have even more than 4 outputs as you're going along. And basically, you're going over the entire data set doing that, trying to maximize the advantage of the model. And so the real kind of secret sauce here is you want to keep the rewards like as high level as possible and let the model kind of figure out the specifics of how to get to that correct answer. And I think the more that you try to enforce what you want the model to do in here, the more likely it's just going to reward hack and like try to optimize for what you want it to do in here and not optimize for exploring the space to get to the right answer. So some example reward functions, we looked at very simple ones like, is the answer correct? Is an XML tag present? You could do things like, does the answer contain a substring, and have that be less of a high reward. You could do if the answer's formatted properly. If you're training an agent to call tools, you could say, did you call the right tool here? And in our case, we're going to be building a coding LLM. So we're going to say, does the code compile and does the code pass unit tests as the reward functions? And so this is kind of the setup that I had for this task, training a small language model on Rust coding. We'd take in a user prompt, have the model generate LLM or generate code to solve it, and then we have a set of verifiable unit tests that we're going to run this code, see if it passes the unit tests, and those are going to be the reward functions that we feed back into the model. And what's really cool is as the model's training, these are the average score over time. And you can see it kind of, there's three rewards shown here. This one is just purely, does the generated code have a code block and a unit test block? This one is, does the build pass? And this one is, does the test pass? And you can see it like learns the format really quickly and then starts to learn how to build and then starts to learn how to pass the test. So plotting these as you're going through your training runs is a really useful debugging tool to see maybe one of your reward functions, it is hacking and it's just getting really good at the formatting, but not getting really good at passing the unit tests. And so the first thing that I kind of wanted to decide on is how small of a model was I going to train? And there's a lot of compelling research coming out that you can get pretty performant models under 7 billion parameters or even down to 1.5 billion parameters. So I kind of stayed in between the 1.5 and the 3 billion parameter range. And for specific tasks, even a 1.5 billion parameter model has been shown to outperform GPT-4o and O1 preview if you're very specific in the types of rewards you want to do. And so I kind of touched on this before, but the big kind of breakthrough in this GRPO setup is we no longer have this value model. And why that's important is the memory usage that you're going to have to figure out how much memory these models are going to take up while you're training them. And I wanted to limit myself to a single H100 for all of these experiments. And so if you're doing a full PPO run, you have the value model, you have the reward model, you have the reference model, and you have the model that you're training itself, the policy model. GRPO drops the value model like we talked about before. It does still have a reward model. You could have this reward model sitting on another machine if you wanted to, or have it be like a model that you're making HTTP requests to. And with GRPO 0, they actually didn't have a separate reward model. They just used the same policy model that they had here to do the rewards. So that even had less memory requirements. But we're going to kind of be in the middle here. And so the first thing I did was, okay, for an H100, where am I pushing the limits? And so I had a 0.5 billion parameter model. These are all Quen models, 1 billion, 3 billion, all the way up to 14 billion. And then I saw, can we do a full fine tuning? Can we do a fine tuning in 8-bit? can we do a fine tuning in 8-bit with gradient checkpointing, or can we do parameter efficient fine tuning? And if you think about a full fine tuning, not only do you have all of the pure model weights themselves, but you have to keep a copy of all the gradients for all of the weights as well. So you might be kind of surprised, like seeing 0.5 billion parameters goes to 25 gigabytes of VRAM, but just remember that we have all of those copies of the models, and then all of the copies of the gradients, and then that across however long the context window is that you're passing in. So this is kind of my sweet spot for an H100 training a 3 billion parameter model, because an H100 has about 80 gigabytes of VRAM. So again, formulating the problem, take in prompts, generate the code, pass the unit tests. And so the first thing that I did was generate a ton of synthetic data for this task. And so I found this data set, ACE code 7087K, but this was all Python code. I didn't find a data set that had Rust input and output examples. So the first thing I did was translate 20K prompts from Python to Rust. So if it had like very Pythonic things like use a generator and yield the results or something like that, try to translate that prompt to a more Rust-like prompt. Then I took all of those prompts and I generated code for them. Then I took all of the prompts and code and generated unit tests for that. And then I took the prompt code, or I guess the code and the unit tests, ran it through Clippy, which is like the formatter for Rust, ran it through build, and ran it through compile. And that gave me a filtered down synthetic data set. And I did all of this in the Oxen platform. You can kind of just put in a prompt, run it over your data set, and generate a new column of data, and then put in a new prompt, run it over your data set, generate another column of data, and same thing for the unit tests. So that was kind of got me to these triples of Rust prompts, Rust code, and Rust tests. And so from there, I wanted to get a baseline of how performant is one of these state-of-the-art models. Did pretty good passing the build, passing the formatter, and not so great passing the tests. And so my first question was, is GPT-4o really that bad at this task? And if I've learned anything over the years, you should definitely just look at your data, not just that number that comes out. And so I put all of this data into Oxen and looked at, okay, let's find all the ones where the test failed and look at the error messages that came out. And what I found was if you formulate the problem like this, where you have prompts, expected generated code, and verified unit tests, if you don't specify what the types are and what the name of the function should be, you have no context when you generate this output of, oh, should this be a floating point 32? Should it be an integer? Or what should even the function be called? And if you're thinking about like using cursor or something like that, you're probably not going to write the unit test definition before you ask it to generate the function. You might, but kind of our problem spec was not well defined for this task. So doing this in 3 steps is kind of hard. So I decided to simplify the problem, just take in the prompt, and then have the LLM generate both the code and the unit test, because that felt more natural of like, I'm working in my text editor, just put in a prompt and then generate both halves for me. And then had a giant system prompt of like what I wanted the format of the output to be and some other kind of stuff beforehand. So ran that again with GPT-4o, got much more numbers like I would expect. GPT-4o could get the test pass 78% of the time given the prompts. So I was like, okay, cool, let's see if we can make this happen with a much smaller model. Skip over this one. So going back to what was our reinforcement learning rubric and reward functions. So we have a prompt that comes in, and this is kind of what we want the output to look like. We want it to have a REST code block. We want it to have one single function, and then we want to have a set of unit tests that have at least a couple assert statements that are different. So my rubrics turned into the response must contain a code block. So that was kind of a regex. The response must contain a test block. The tests must have assert statements. So if they don't have assert statements, it would just pass because there's like nothing for it to check in there. Then the cargo build needs to pass, the cargo clippy needs to pass, and the cargo test needs to pass. So again, thinking of the has unit test as an example, and if you look at the code back here, this is kind of the test block down there. So that was just a simple regex of like, does it have the right format for the unit tests? If so, the reward's 1, else the reward's 0, and do that for all the prompts and completions as you're going through training. Putting that back into our GRPO trainer, which we looked at before, which was like kind of 10 lines of code to set up. Now we're passing in each one of these reward functions, and I played a little bit with like, is the test passing the most important thing, or is the compilation the most important thing? This is kind of the hyperparameters I settled on. And I wrote a nice monitoring script that would log all of these to Oxen like we saw at the beginning, so that I could plot per reward function how was the model doing. That also allowed me to look in as it was generating each one of these examples. So you might have task, 144, it generated 4 responses, 3 of them it got wrong, 1 of them or 2 of them it got right, and I could look at the inputs and outputs as it's training, which helped me figure out, the first iteration I did of this, I didn't have the must have an assert statement in there. All the unit tests were passing, but it was just like putting a single comment in there instead of actually having assert statements. And so that helped me iterate on what the actual reward function should be in there. And so started with a 3 billion parameter Quen model and just wanted to get a baseline. It actually did a pretty good job of passing the build and passing the Clippy formatter, like 80% of the time. Only passed the tests 37% of the time. So this is Quen 1.5 billion and the coding specific one. After one epoch of those 6 reward functions, got all the way up to 73% writing the code and passing the unit tests. And so if you remember, that's starting to get in the ballpark of GPT-4o and on a single H100 for one epoch with not that many very specific reward functions. So that was pretty encouraging, and I think it really leads to you should try these things yourself. Like these models or these approaches are very approachable these days, like 10 lines of code, like I said. It's pretty easy to generate your own synthetic data with some of these models. It's pretty easy to build your own reward functions, and I did this in under what it would cost for our free credits for your GPU in Oxen. So I have all of the code right here, which is what that QR code goes to if you want to check it out on GitHub. And that's it.